My name is Stefan Borton. I work as a staff scientist at RHK Technology, and I've been involved in any project that has signal processing and embedded systems in it for the last 19 years. The company RHK was founded in 1981. In the beginning, we built spectrometers and temperature controllers. In 1987, we built the first commercially available STM controller. Those were the days when images were plotted on an XY chart recorder. If you have a look at the first publication of Binnig and Rohrer, the images in there, there are these line plots on a chart from a chart recorder. That's like our controller was the same. In 1994, we introduced the Beetle STM. This microscope has 3 legs and kind of crawls up and down on a spiral ramp for approach. This 3-leg microscope is very stable, has very low drift, low noise, and high resolution. It's together with the vacuum system that we sell, it is extremely flexible and expandable for all kinds of experiments. In 2001, we added AFM capabilities to this Beetle microscope. It converted it into a variable temperature AFM. And this microscope can now be run with cantilevers and with Q+ non-contact AFM sensors. That's this microscope. We have 2 more lines of products. The other one is the PanScan Freedom cryogen-free SPM. It can be reach atomic resolution in the range from 9 to 400 Kelvin. We have successfully demonstrated this at conference booths and different occasions. This is an HOPG image taken at low temperatures. Unfortunately, it's a little small, but if you go to the website, I'm sure you'll find a bigger version of this picture. What I want to talk more about today is the R9.5 SPM controller. This is a fully integrated one-box solution, meaning that there is amplifiers, lock-ins, as well as high voltage amplifiers for the probe drive, all in this box. It has ultra low noise, high voltage outputs. It has 2 phase lock loops that can be linked or can be completely independent. There's a PLL lock guard that watches the PLL's performance, and we can do time-based data acquisition. That means that the data is not triggered by image position, but by time, and I'll get into that a little later. And we have a full diagnostic suite. Now, why do I talk about control electronics? We want people to know their instruments and their electronics because we think that you can only do your experiments well and design your experiments well if you know the machines that you use for the experiment. We want you to be confident in operating it, and we want you to be able to interpret symptoms for diagnose if anything goes wrong. We frequently find that for many people, lock-ins and particularly PLLs are black boxes that they don't really know that much about, and that is what I'd like to change today. The first part of this presentation will be about feedback control systems. This subject is seen by many people as gray theory and very abstract and hard to understand. And in order to prove the opposite, I'd like to start with a little anecdote. Who of you has experienced this before? You're far away from home, in a hotel, at a conference, 7 o'clock in the morning, the alarm clock rings, you crawl out of your bed, get into the shower, turn on the water, and it's very, very cold. Now you turn the hot water a little more, and suddenly there's boiling water coming out of the pipe, right at your skin. You turn the knob down, and the water is freezing cold immediately. You step out of the shower, and then you start thinking, what went wrong here? Now, the shower, and you in the shower, is a control loop. There is a sensor, that's your skin. There's an actuator, that's the valve, the warm water valve. And there is what in control theory is called a plant. That's the water pipe going up to the shower head, and probably also the water coming out of the shower head onto your skin. In your mind, you have a temperature that you want the water to be. That's called the set point. You compare the temperature measurements from your skin with that set point, and depending on whether it's too hot or too cold, you turn the knob for warm water open or close. The problem here is, how much gain do you apply? How hard do you have to turn the knob when the water is how much too cold or how much too warm? And obviously, you have used a way too high feedback gain, so you've turned the knob way too much. There is a delay in the pipe. The water takes a little bit of time to climb up in the pipe. So when you turn the knob too far, it takes a little while, and in that little while, you've turned way too far, and that's why the water is too hot and too cold. You will learn very quickly that you have to turn that knob very slowly, and then everything will be fine. That learning is called adaptive control. Now, there's many control loops all around in your life, around you. Just the fact that you made the turn into the bathroom for the shower is control life, is control loops. The fact that you can breathe, that your pH value in your blood is kept constant, the fact that you can walk, you can stand, all is control loops. I dare to say that control loops are the essence of life. No life would be possible without any control loops. Actually, humans are very good at judging controls. You are very good at seeing when somebody is drunk, when he has his control parameters affected by some alcoholic beverages. You can see that immediately. So these are very complicated feedback loops, and humans are able to judge them within a split second. So I'm very surprised that people have so much difficulty understanding the very simplest, or the second most simple control mechanism that is available. That is the PI controller. Now what happens here, this is a graphical depiction of the feedback algorithm in our PI controllers. We have an input in the shower. This would be the measurements from our skin, the temperature measurements. We have set point. I told you that's the temperature we have in mind for the shower, what we find nice and warm and good. The deviation, the difference between the two, is called the error signal. Now, the very simple, most simple control algorithm just multiplies the error signal with a proportional gain and outputs this to the output. And the output would be the valve that we turn. Don't look at this. Just think of it as a straight line here now. I'll talk about this section of the PI controller later. So the first, imagine we only have a proportional controller. Don't even look at this. Then our error signal will be amplified and output to the valve, of our shower. Now, this has a problem, and the problem is that imagine our input reaches the set point, then the error signal will be 0. If we multiply 0 by a proportional gain, then the output will be 0, and the valve will be completely closed again. This can't be true. So what this means is that a proportional controller can never make the input equal to the set point. There's always a deviation, and that deviation is needed to keep the valve at a certain position. This is called the steady state error. And in order to fight the steady state error, people have introduced an integral gain. For the integral gain path, our error signal gets multiplied by an integral gain, and then it gets added up. This is the digital representation of an integrator. It's called an accumulator. What happens here is your I times error gets added into a number and then stored here, and the storage is then added into the next iteration of this. So this is kind of an integrator in the digital world, and then the integrator output will be added to the proportional gain, and that's our new output. And with this integrator, the integrator will crawl up and down as long as there's an error signal, and that will compensate our steady state error. And now we're able to reach the set point, so control the input so it exactly reaches the set point, and the error will be 0. So in a mathematical equation, it's written like output equals proportional gain times error plus integral gain times integral error dt, with E being the error. This is very nice. It works very well. However, there's a problem that we have to adjust both the P and the I gain, and particularly on the PI controllers in the PLL that have to maintain the phase and the amplitude. I'll talk about that later. this is very difficult to adjust. So we have made a simplification for the user that unfortunately looks a little more complicated here. The PI controller is exactly the same thing that we show here. However, we present some slightly different parameters to the user. There's a parameter K, which is equal to P. That's this K. And there's a parameter FC, which is the integral cutoff frequency. That's integral gain divided by pi times P gain. And if you fill this in here, you get output is K times error plus pi integral cutoff times integral error dt. If you multiply this out, then you get back to exactly the same equation here. However, there is one trick, and the trick is this: FC is equal to the width of the resonance peak in the cantilever amplitude resonance. If you set that the same value, then you can prove that the controller cannot oscillate. And we end up with only one parameter K, and that K is very easy to adjust. I'll show you later. It's just basically moving a number up and down until the step response is rectangular. That's very easy to adjust. Now, open loop response, if you just take the controller and take away the plant, that is quite often used for checking the loops. So what we do is there is no feedback, the loop is open, and we apply an error signal at the signal input. And then we check what the output of the controller does. So because we have the proportional gain, if there is at the time t here, there is a change in error signal, then there will be a step in the output because there is a proportional gain times the error. And then from that moment on, the integrator will slowly run up. And the rate of running up is integral gain times error per second. So every 1 second, the line crawls up, integral gain times error. And this will run up until it reaches the limit. And we'll talk about the limits in a minute. I told you to ignore this for a moment. This block shows the upper and lower limit, the output clamp. It's useful to clamp the output not just to the upper and lower voltage rails, but also to limit the output at certain levels. This way you can sweep the output of the PI controller to any value that you want. You can reset the controller to the center. You can retract the controller to the very top level. That's all possible with the help of this upper and lower limit. And they act like a kind of a tweezers that kind of grab the output and move it up and down to any value you want. Between upper limit and lower limit is the only range that the output can go. This is done by calculating back on the summing point of the integrator. So if our sum here exceeds the limit, either one upper or lower limit, then we'll change the summing of the integrator in a way that it will not exceed the limits anymore. So this has a consequence that whenever you clamp your output to some value and you open the loop again, remove the limits, then the integrator will start from that value. Now, if you want to run a pure proportional gain, that might be a little confusing because at an error of 0, then there will be still some value in the integrator and the output will not be 0. So for a pure proportional gain, you should probably reset the upper and lower limits first. This brings me to our PI controller block. In all schematics that I draw later on in this talk, there is this PI controller block used. This is the input. The input is compared to the set point, and then there is an integral proportional gain, or the K and cutoff used here for this, and the output of the PI controller is then drawn like this. So we'll use actually 4 of these in the most complicated feedback schemes. Now let's have a look at the signals that go into the microscope head and come out of the microscope head. We have a digital controller, so I depict this here as a digital to analog converter. There is some amplifier behind this. I don't really care at this moment about this amplifier. Generically, the DAC output oscillates the cantilever. Also, the method of oscillating the cantilever, of shaking the cantilever, is not important for me right now. It can be optical, it can be mechanically, it can be electrically driven. It doesn't matter for what we're talking about here. Then at the cantilever, there's a detector. This can be an interferometer, this can be beam deflection, STM tunnel tip, anything. We don't care about it. It produces a signal, and that signal gets digitized, and then we plot it here. So the drive signal of into our microscope head will be a sine wave signal, and then the detected signal will also be a sine wave signal of the same frequency. If the system is in stable conditions, the detected frequency will always be the same frequency as the drive frequency. This is very important for later on. The microscope head does not invent any new frequencies, at least when it's in a stable regime and linearly interacting with the sample. Now let's have a look at oscillations. From school, you're used to plot oscillations as a signal X over time, and you're using a sine or cosine wave to plot the oscillations. Today, I'd like to introduce another view on the same oscillation, and I'd like to view it as a complex signal. So what we're looking at here is the X over T diagram, but there's also a Y over T diagram. And if you rotate our view a tiny little bit, you will see what I mean. Then you have the time, we're looking at the time axis right now, and then there is an X and a Y signal. So our oscillation is actually a spiral. This is plotted here. So our oscillation is this e to the power of I omega t, which in fact is a spiral. And we're used to looking at it either from the view of the real axis or from the imaginary axis, and then we get the projections. If you look from this side, then you get the sine wave, which is the imaginary axis over time. That's the sine wave. Or you look from the top, then you see the x-axis, which is the real axis over time. That's the cosine wave. Those are the two waves that we use to, or the two functions that we use to describe oscillations with. And I like to combine the two now into a complex signal. That's this spiral. Now, if you look at this spiral from directly look at the time axis here, this axis is angle, is plotted here as an angular axis, of course, for the sine wave, but it's also a time axis for the oscillation because the angle changes with time. So this is the time axis. Now, if we look straight into the time axis of this 3D plot, then we'll get an image like this. So our e to the power of I omega t is a circle, and the sine and the cosine waves are just look flat on. They're just stripes here. This is the way I'd like to look at oscillations for the remainder of this talk. It's called a Phasor diagram. A Phasor diagram looks like this. We have the x-axis, we have the y-axis, we have a vector with a length. That length is the amplitude of our oscillation. And we have a phase angle, that's this angle. And that phase angle is defined as 2 pi f or omega t, and t is the time. This means the angle constantly increases with time. So our vector actually spins around here. Of course, we were talking, if you think about the previous pictures, we were talking about this spiral. So our vector has to go along this spiral, and it will constantly spin around this circle. So there's four things that we can talk about here. There's the x component. X is amplitude times cosine phi. There's the y component, is amplitude times sine phi. There's the amplitude, and there is the phase angle, as I said earlier, and then the phase angle depends on time. I had an idea how to describe this while sitting watching the Berlin 6 days in the velodrome. This Phasor diagram is exactly the same as what happens in the velodrome. There are these bike riders. You can think of a vector from the center of the stadium to each of the bike riders. At any moment, they have a certain phase angle. The zero line for the phase is here, the finish line. And they can have different lengths, so they can be further out or further in. That I would call the amplitude. The only problem with the velodrome is that it's not circular. If you assume it's circular, it'll serve nicely for explaining further on what I like to show you. We have to think of a new way of defining frequency for this. If we look at the phasor diagram, the phase constantly changes. The vector actually spins around. So if we define the speed of change of the phase as frequency, so frequency equals d phi over dt, then our unit for this will be degrees per second. If we divide that by 360 degrees per cycle, then we get cycles per second, which is hertz. This is a way of defining the frequency. So the frequency is actually how quickly the phase changes. So and this frequency can change within a cycle. If you think about the velodrome, the bike rider can go faster and slower along the track. So his speed of change, his frequency, is momentary, instantaneous frequency. It's called instantaneous frequency. This can change during one lap that he runs around. Now, in contrast to this definition is the definition that we're used to that comes from the Fourier transform. In the Fourier transform, the frequency is defined as 1 over t, t being the period time of the frequency. So in order to measure the frequency, you have to wait for at least one oscillation period. There's no way you can talk about frequency before you've measured one oscillation period. This frequency does not change over oscillation cycle. Actually, in the Fourier transform plot, everything is represented as fixed frequencies. And if a frequency changes, then this shows up as sidebands in the spectrum that also have fixed frequency. So in the Fourier transform way of defining frequency, this is a very fixed thing, whereas our definition of frequency, the instantaneous frequency, can change very quickly. This is a very different concept because with an instantaneous frequency and with an instantaneous amplitude, you can basically describe any function that's periodic. Another thing that I like to talk about is that frequencies can be negative. In our instantaneous frequency definition, that means that the phase speed, or the d phase over dt, is negative. This means the vector turns around the other way. In the velodrome, this would correspond to a bike rider cycling counterclockwise against all the other ones. It's forbidden there, but in our world, it's a very useful thing to have. Next, I'd like to introduce you to my oscillator block. The oscillator produces a sine wave and also a cosine wave, but that's not drawn here. A sine wave with a maximum full-scale amplitude, digital full-range amplitude, and we multiply this full-scale signal with a certain drive amplitude. This drive amplitude is between 0 and 1, and that way we can produce any kind of drive amplitude here. So I separate the sine wave generation from the amplitude setting in these two blocks. The oscillator itself has an internal parameter, that's the F0. This is the called center frequency of the oscillator. And then there's an input, and this input can be used to sweep the frequency up and down, or to basically create a frequency deviation from this F0. So this dF can be slightly positive, can be slightly negative. If this dF is 0, the oscillator goes at exactly that frequency. If that dF is, I don't know, a hertz next to it, then, or is 1 hertz, then this will be 1 hertz plus F0. This allows us to sweep the drive frequency and basically plot the response of our microscope head cantilever system to that frequency sweep. And the result of this, you all know, it's the amplitude resonance and the phase resonance. At exactly the resonance frequency, the amplitude has a maximum. There is actually two resonances. One is the amplitude resonance, and the other one is the phase. I call the phase resonance. For low Q cantilevers, they are separate. For high Q cantilevers, those two resonances are very, very close together, so they appear like the same thing. The amplitude resonance, however, is always a little bit lower than the phase resonance. The phase resonance is where minus 90 degrees are reached between the drive and the detection. Now, I'd like to show you this also in the Phasor diagram and also in the velodrome analogy. So for low frequencies, far below the resonance, the drive signal is always the one here on the circle, and the detected is the other vector. Both vectors spin around. I have a resonance frequency of about 2 megahertz here, so they go around 2 million times per second. At this frequency, I don't know, 450 hertz below the resonance, they both have the same phase. There's 0-degree phase difference between those two. So there's two riders in the velodrome. One is riding very much inside on the inner edge, and one is riding in the middle of the track. If you go to this spot, then the drive is still depicted here as on the circle. The detection has a much bigger amplitude, and it lags behind by 90 degrees. Keep in mind, both vectors are still spinning 2 million times per second because we're in a bike race. Again, this is two bike riders. One is riding in the center of the track, and the other one is a quarter lap behind and is riding on the very outer edge of the track. Just picture it like that. If we increase the frequency further, then our drive and the detection have a minus 180 degree phase shift. That means they kind of point into exactly the opposite direction. In our velodrome, this means that the drive and the detection bike rider have a half a lap difference, and the detection bike rider rides on the very inside of the track again. Again, keep in mind, we're spinning. It's running around. Now, in order to analyze it, we'd like to get rid of the spinning. The spinning is the problem because you can't really see the bike riders. They zip by so quickly you can't really see what they do. So the idea is we just counter-rotate the track in the velodrome. It's a very crazy idea. Looks like this. So this depicts the track in the velodrome. You see the bike rider. Underneath the bike rider, I put a big motor that spins the table that he's running on. So now the bike rider can ride any speed. If we set the motor to any speed, we can basically make the bike rider go backwards, can make the bike rider go forward. It doesn't matter. We can always set it. This process is called mixing. So by mixing, we'll coordinate rotate our reference system for our complex input signal, and the output signal is then a signal of different frequency. And if we set the reference frequency correctly, we'll exactly make things stop, and we have a fixed phase relation between those vectors. So in the velodrome, that means we can really keep the bike riders at one spot, and we can watch their phase relation between each other nicely. So the logic for this rotation is pretty well known. It's the simple math coordinate rotation. X dash is x cosine phi minus y sine phi. Y dash is x sine phi plus y cosine phi. X dash and y dash are the outputs, and x and y are the inputs. So these are the outputs. These are the inputs, and phi is the rotation angle. You can also write this in complex form as x dash plus I y dash equals x plus iy times e to the power of I phi. That's equivalent to this, according to Euler. Now, we have one problem. This is all very nice. We have one problem now. That problem is we dreamed of having a Y signal, but there is no Y signal. Our detector only produces a real signal from the real world, and there is no imaginary signal. So there's nothing else that we can do but feeding a 0 into the Y. If we do that, then this term and this term both will be 0. And the mixing will come down to just 2 multiplications. That's depicted here. So our X signal gets multiplied with cosine phi and with sine phi, and that gives us the X dash and Y dash. Doing this, we've cut a corner. And for cutting corners, you usually have to pay. And we pay this by a misunderstanding. The mixer will interpret our signal in a slightly different way than we anticipate. Imagine this black dot here. That's our input signal, this black dot here. And what the mixer input understands of it is actually 2 signals. because there has to be a Y signal. These two signals counteract. Their X coordinate at any time adds up to our black dot, and their Y coordinate at any time compensates to 0. So the sum of those two complex rotating vectors here, the vector by vector I mean from the origin to each one of the dots, the sum of those two vectors is always the black dot. So my point here is our real only input signal will be interpreted as a positive turning half amplitude frequency and as a negative turning half amplitude frequency. If any of you has ever tinkered with a Fourier transform, you know that if you feed a real only signal into the Fourier transform, you get a positive peak and a negative peak, which both have half the amplitude that you inserted. That's exactly the same story here. The Fourier transform, as well as the mixer, expects a complex signal, which is called an analytic signal. An analytic signal is this sine and cosine. And if it doesn't have it, it interprets, or if you feed only a real part of it, then the imaginary part is basically misunderstood as these two peaks of oscillation. Now, if we look at this mixing process, before the mixing, at the input of the mixer, we have two signals now because of the misunderstanding. There's the clockwise and the counterclockwise rotation of those two vectors. There's also a DC offset. So imagine on our bike track in the velodrome, there's two bike riders. Illegally, one is riding the correct way, and the other rider is riding the opposite direction. And then there's some service person sitting on the track that has that's the DC offset. Now, if you spin the table, and if you spin it at the correct frequency, the same frequency that the bike rider goes, then our minus F0 peak will be shifted to 0 frequency, our DC offset will be shifted to F0, and our counterclockwise riding bike rider will have a double frequency, so he will go around at double speed. This F0 part will cause some issues with filtering that I'll talk about later, but I'd like to introduce it right here now. And as I said, and it's probably obvious that the frequency, the phase angle here is constantly changed with time in the mixer. That's kind of represented by mixing with the sine and the cosine omega t. Now that we have our mixing product here on the left side, the peak at 0 frequency, the peak that's caused by the DC offset at the cantilever resonance frequency, and the 2-off component. We'd like to get rid of these two, and that's done by a digital or analog filter. These plots are done over a frequency axis. A filter basically is a frequency-dependent gain. The low frequencies have a high gain here of 1, and the higher frequencies then have lower gains and get attenuated. So this way, most of the time, we can get rid of the 2F component and probably also the 1F component. I left it in here a little bit to make a point later on. And the main signal contribution is from the static part that does not rotate around anymore, and that allows us to measure an X and a Y signal and a phase and an amplitude, and the phase will be fixed. One note about cantilever resonance frequencies. From this picture, you can see that it's an advantage to have a high cantilever resonance frequency, because then these peaks are far away and it's easy to filter them out. If you have a low cantilever frequency, and by low I mean something below 20 kilohertz, then this filter has to be much sharper, which will result in a much slower response and a much slower microscope later on. This is the whole lock-in block. We have our mixer here. We're feeding our input signal into the X of the mixer. There's a 0 in the Y, or we're actually using the scheme with the 2 multipliers that I showed you earlier. The reference comes out of an oscillator. This is actually 2 wires, a sine and a cosine, as you've seen before. And then we get the X dash and Y dash, which is the unrotated version, which actually has the 3 peaks that I just showed you in the previous slide in them. they need to get filtered, and then we have the X and the Y signals available. And from the X and Y signals, we can calculate the amplitude, which is the square root of the sum of the squares of the two, and the phase angle, which is the arctangent of Y over X. So our lock-in now has 4 output signals, the X and the Y, and the amplitude and phase, which are exactly the same that I showed you in the phasor diagram before. By the way, the X and Y are an analytic signal here. They are 90-degree phase shifted all the time. In reality, we actually put an offset here and there that allows us to get rid of static vector offsets on the inputs, but that's just a small detail. This all is done inside an FPGA chip. FPGA chips have the advantage over processors that they can run processes massively parallel. The best processors today that I know, they probably can run 8 or maybe 16 threads at the same time. An FPGA chip can easily run hundreds of thousands of parallel things at the same time. They can be very simple things and they can be very complicated things. This is always described in the hardware description language. We use VHDL for this. Now, implementing this in an FPGA chip has a consequence that everything is clocked. There's clock frequencies for everything, and there's different. The one thing I'd like to show you here is there's different clock domains. There's a 100 megasamples per second clock domain. That's basically the ADD converter and the input here. The mixing is done in the 100 megasamples per second clock domain, and also the oscillator output is in the 100 megasamples per second clock domain. The other side of this picture is the 200 kilosamples per second, which is a 500 samples slower, or 500 times slower than this. That has all the signal outputs of the lock-in, and that also has the delta F input into the lock-in. The transition between those two clock domains is done in the low-pass filters, and it's called decimating. What happens here actually is we're kind of averaging the samples together, so 500 of these samples together make one of these samples. And this is the reason why in this lock-in amplifier, the two filters are the most complex pieces. Everything else is pretty simple. The filters are really complex, and they're tricky and complicated, and the filters actually create the dynamic reserve. If you make mistakes there, it shows up in noise peaks that are really hard to track and to detect. So for this reason, because the filters are the most complicated thing, we also use the lock-in amplifier for static mode detection, for tunnel current detection that has a DC input here. The only thing we do is we put the oscillator to a frequency of 0 and a phase of 0, and then the X dash will be the same as the X. We just filter it and now put it here on the X and feed that into the ZPI input. So the decimation still has to be done because we need to get from the high data rate to the low data rate, but no lock-in is done in this case when we have a DC input. With the next two slides, I like to show you why lock-in amplifiers are useful and what their strengths are. If you look at this, it's a plot of signal versus frequency. This axis is frequency, this axis is an amplitude, a detected amplitude. And the light blue here is the noise. We have some kind of white noise here of the big frequency range, and as soon as closer as we get to the DC value, to a frequency of 0, there's short noise and 1 over F noise that increases as we get closer to 0 frequency. Now, if you want to detect as a very small signal, say 350 nanovolts, then your noise actually integrates up in the bandwidth of your detection. So if you have an amplifier that detects from here to here, then all this noise will integrate up and will completely drown the peak, and we won't be able to measure it. The solution to this would be to make a narrow filter around here, so we pick up very little noise of this much smaller bandwidth. But it's very, very difficult to build a filter with a bandwidth of, say, 100 hertz at around a frequency of 1.018 megahertz, and to make this precise, it's very, very difficult. So it's much easier to convert this down using a mixer, as I described it before, and then put the filter here to around the DC value, which is actually what the lock-in does. Now imagine we have two signals here. One signal is very little. I remember on the last tests I did, it was 350 nanovolts. And we could deliberately put another signal of 0.8 volt, which is huge, next to this 350 nanovolt signal at 2 megahertz. So they're quite far separated, and these are really pure sine waves. For this test, the trick or the difficult thing is to really use a pure sine wave without any harmonics or distortion in it. When you do that, it's possible with a good lock-in to detect the 350 nanovolts 1 megahertz oscillation on top of a 0.8 volt 2 megahertz oscillation. The lock-in can very easily separate that. And this capability of a lock-in to separate two signals of different frequency and completely different amplitude is called the dynamic reserve. In our example here, the dynamic reserve will be 127 decibel. Another nice feature of a lock-in is that it can measure slopes. You remember from math classes that the slope is usually calculated as delta y over delta x, according to this formula. This is an approximation. It's not the derivative. The derivative is calculated by making these deltas very small, but we'll here approximate it by delta y over delta x. And if you now look at a signal, and we're driving the signal here, for instance, a voltage, there's a DC offset on the voltage, I'll call that x0, and we are modulating this voltage around x0 by an amplitude D, which I call D because it's a drive amplitude, and then we're detecting another amplitude at that frequency that we're driving here using a lock-in. So the lock-in will be invisible, the DC signal will be invisible to the lock-in, and the lock-in will actually detect this amplitude. We know this amplitude, and we can easily calculate an estimate for the slope here out of this lock-in measurement. This nicely works also for higher modes with the double frequency here, and this is the basis of higher harmonics multi-frequency measurements on nonlinear interaction processes. So our lock-in amplifier can be described in the cartoon world as the bike rider on the rotating track, and we're putting a scientist here on a chair that has a telescope, this thing pointing at some spot on the bicycle where there's a crosshair, and there's another crosshair in the telescope, and our scientists can now detect whether the bike rider runs ahead or runs a little bit behind in rotation phase. This leads us to another subject, and that is a lock-in amplifier is used for homodyne detection. Homodyne detection means we know the frequency of our instrument. We know the frequency that we drive our instrument with, and therefore we know the frequency that comes back out of the instrument. And we know they are exactly the same. There cannot be any difference in frequency. There can only be phase differences. So if the bike rider goes exactly the same frequency or the same revolutions per minute as the motor returns, then we know we keep the bike rider at the stop position, and there can only be phase angle shifts between them. And the phase angle shifts are what we're measuring in this homodyne detection. Things will be very different when you think, for instance, about a radio station or receiving a radio station. The radio station has a frequency. That frequency is known, but it's not known exactly. And there can be differences in our reference clock and in the reference clock of the radio station. So we don't know exactly what frequency the radio station will send. So we can, in our picture here, this means that we don't know how fast the bike rider will go, and we have to set the motor accordingly. So the relation between the two is broken in this example. And that problem leads us to a solution, and the solution is we're controlling the speed. We're controlling the speed of the motor. So our scientist here gets a little handle, and he can now control the speed of the motor. And he can see the crosshair on the frame of the bicycle in his telescope. And when the crosshair shifts left or right, he can then speed up or slow down our motor. And you see, this is a feedback loop. And this feedback loop is called a phase lock loop because we're locking the bike rider at its position. We're locking his phase. Phase lock loops have been in use for many years in radio receivers. You probably have seen PLL radio receivers for FM. And that's exactly the same thing. The signal that you're taking out of your radio receiver will basically be the position of this handle. If the bike rider goes a little faster, then the control loop, our scientist here, will have to switch the motor a little faster. So this handle here will be at any time a measure of the momentary frequency or of the instantaneous frequency of our bike rider. And we can plot the frequency, the instantaneous frequency of our bike rider just by connecting a signal here to a plotter. There's also other possibilities. You can run a second table at exactly half the frequency and generate half or double or triple or any multiple of the frequency of our bike rider. That's also used in a lot of applications technically. So the idea of this is we're controlling the position of our bike rider here by speeding up or slowing down the motor, and this is then our delta F signal. As an example for a phase lock loop, I'd like to show you this block diagram of a frequency modulation radio receiver. It's actually an amplitude modulation radio receiver as well. So there's an antenna that detects a signal from a radio station far away. There's some amplifier here that I don't care too much about at the moment. There's an analog to digital converter. It goes into the input of our lock-in. Lock-in produces an amplitude and a phase output. And we've set the lock-in to our frequency of the radio station. Imagine the radio station is 107 megahertz. We'll set the lock-in to 107 megahertz. And we'll get an amplitude and phase out of it. If we're setting exactly the same frequency, then our phase will be fixed. And if our frequency is slightly off compared to the frequency of the radio station, then the phase will start turning around. And this turning around is detected as a deviation from a set point in a PI controller. And the PI controller then creates a delta F word that's added to the frequency of our lock-in. And that keeps the frequency of the lock-in always exactly at the same value as the frequency of the radio station. And the control signal, which is the handle of our scientist, if you remember from the last picture, that's this wire. That is our frequency modulation output. And when you do that, you can at the same time also measure the amplitude modulation, which is at any time the instantaneous amplitude of our signal. Now with this, we have to look at our cantilever resonance plot again and at the phasor diagrams. There are in these phasor diagrams, there are three things actually, three oscillations. One oscillation is the drive oscillation. That's this one, I showed you that before. The second oscillation is the detected signal, that's this one. And the third oscillation is our reference of the mixer. It's basically how quickly we counterspin the table or rotate the coordinate system in order to make these vectors stop. Sorry. But we know exactly what frequency we drive into the system. So we know exactly what frequency we need to spin the table. This is a homodyne detection. However, depending on the frequency, if we change the frequency of those two, then our detected signal will vary in phase position, and it will vary in amplitude also. And we're setting our phase lock loop. We're detecting actually the phase of this detected signal in relation to those two, which are combined, as I said before. So we're setting the set point for this to minus 90 degrees, which is here. And our phase lock loop will basically keep this position where the detected signal is 90 degrees behind the drive signal, which is coupled to the spinning of our table or to the unrotating of our coordinate system. This is the position where our phase lock loop will keep the drive signal. Now this is how the phase lock loop will look like in our instrument. We have our cantilever again with detector, amplifier, ADD converter, and input. We're detecting amplitude and phase, and the phase signal is then fed into a phase PI controller. We call it PLL PI, and the delta F output goes to the drive oscillator, and it goes to the reference oscillator in the lock-in. There are two oscillators. I told you there's an oscillator in here, and there's another oscillator here. You might ask, why are you using two oscillator and not a phase shifter? The reason is an oscillator is much easier to implement than a phase shifter, and they're easier to uncouple, and we can also run double frequencies here. It's much easier this way. I also explained to you the drive logic here, the drive amplitude creation. That's it. So the set point here is set to -90 degrees. So the phase lock loop will do its utmost to keep the cantilever, keep the phase shift between the drive and the detection at -90 degrees, and that means keep it here at this position. So whenever the peak shifts due to interaction between tip and sample, then this phase will try and change, and our drive frequency will immediately change to keep us at this position. It will lock the phase. This is constant drive mode because we're not changing the drive amplitude, it's constant. That this means our detected signal will vary depending on the interaction between tip and sample. If we put another PI controller here behind the amplitude and feed that back into the drive amplitude, then our system will look like this. This is constant signal mode, so there's a PLL as I described it before, and then there is an amplitude controller where you put a set point. This sets the amplitude that you want, and the drive will then do its utmost to keep that or to maintain that amplitude. This is the phase lock loop that we're using in our non-contact AFM controllers. And as it is a little bit complex, we simplify it and just put it into the symbol. So there's an ADC input into it, there's a drive output of the AFM PLL, and we're detecting an amplitude, a phase, a drive amplitude, and a delta F. And as these feedback controllers for amplitude and phase can be limited on their outputs, we can basically also set them manually to any value, and thereby create a constant drive or constant signal or constant phase or variable phase modes, whatever is needed. This block can even be used as a lock-in amplifier. The next thing I'd like to talk about is tuning, because these feedback loops for phase and for amplitude need some tuning. What we do is we'll periodically kick up and down the set points for a little bit, and thereby forcing the controller to correct this deviation. So we're artificially creating an error signal, and the controller and the whole loop then has to respond to this and adjust. And by looking at how quickly the system adjusts and whether it overshoots, we can tell whether our feedback gains are too high or too low. So this here is the PLL. We're looking at the phase here and at the delta F. The phase is the input of the PLL PI controller, and the delta F is the output of the PLL PI controller. Now you see, we're asking, the phase is originally at 0. When you switch off this test, the phase will be at 0. And we're commanding the phase to go up to 10 degrees and then back to 0. And when we command the phase to go up, that means that the bike rider on our velodrome suddenly has to go to a different phase position. He just suddenly has to move somewhere else. So he has to become a little quicker or a little bit slower in order to get to the newer position. And that you see in the delta F signal as a change in the instantaneous frequency. So this shape here we call the shark fin, and it tells us that our gain is too low still. When we increase one more, now the phase pretty much hops right away to the 10 and back to 0. and the frequency changes are just small spikes here where the system has to catch up or to stop for a moment to get to the other phase position. This is actually a little bit overtuned. As you see here, there's some small overshoot already. I just wanted to demonstrate how this looks like. So this is too low. This is a little bit too high. With the optimum is just slightly cut off here, just a tiny little bit. And this is all done by just changing this K parameter of the PI controller. The ITC is set to the 3 dB width of the peak, which is fixed. So we can do this with one parameter. It's a really easy thing to tune. This was the PLL, and now we tune the amplitude also. With the amplitude, we do the same thing. We tell the amplitude to become a little bigger, to become a little smaller. So there's 100-something millivolt amplitude on this cantilever already, and we tell it to hop up to 110 and back to 100-something. You see here, this is the drive amplitude, that the drive amplitude gets positive and it also gets negative. So what we do is we actually invert the drive in order to quickly take energy out of the cantilever. This affects the Q factor of the cantilever for a moment. We're just dissipating energy here by inversely driving the cantilever. This is a nice feature that is wanted by ultra high vacuum, because for the operation of ultra high vacuum, because when the cantilever touches something and starts ringing, you want to counteract that ringing and calm it down to get to the steady value that you can work with. The disadvantage of this part of this logic is that on a tip crash or when the tip touches the sample, it can happen that the amplitude control loop inverts, because amplitudes are always positive. This is a contradiction in amplitude and in a negative number. By definition, amplitudes are always positive. And when you're so the amplitude, the detected amplitude will also measure a positive amplitude even when you drive negatively. But in that case, our feedback loop polarity is inverted, and it starts to ring up and drive the cantilever really hard. I had a customer call me for this, and I had him on the phone, and he said, "Stefan, your controller screamed at my cantilever, and now my cantilever is gone." This was a cantilever with a Q factor of about 200 or 300,000. So when you drive them with 1 volt output, then they fly away. So this effect that you can actually inversely drive the cantilever is the reason why we introduced our lock guard. The lock guard constantly watches the PLL and checks whether the phase is correct, the detected phase is correct. And if the phase runs out of a range that you can set, by default it's set to 40 degrees, it will pull back the tip for a couple of nanometers and then try to lock in the cantilever again, lock in the PLL again, and adjust the amplitudes correctly and set the Kelvin controllers correctly and things like that. With this lock guard, it's not possible to inversely drive, and it's safe. I just want to warn you, do not run a microscope in ultra high vacuum with the PLL with the lock guard disabled. Actually, what we do is when you disable lock guard on the R9, the amplitude will not drive negatively. It's disabled then. So now we have our PLL block. The next thing we have to add is a ZPI controller. That's the third controller that takes our delta F signal. Some people use the drive amplitude also, but you can also use amplitude or phase. Anything is possible. Feed that into the topo PI controller, and that will then move the ZPAs up and down. So this is the whole story of a non-contact AFM controller. In the next section, I'd like to discuss some common pitfalls, problem that I have seen many people struggle with, and I'd like to show them to you so you don't make these, so you see the reason for these problems and fix the problems before they cause you big troubles and time delays. The first thing is crosstalk. This happens when your drive signal in the microscope head gets somehow capacitively or magnetically, whatever, couples into the detection lines. What the result is basically a steady amplitude over the whole frequency range. This amplitude does not depend on frequency because it's just crosstalk and it's just capacitive and there's no resonance in the crosstalk. This crosstalk signal will be phase shifted with our detection signal, and there are certain spots where it cancels out the detected signal or weakens the detected signal. This will have dramatic consequences on the phase curve. Now, I've simulated this here a little bit, and I've been able to make a phase curve like this. Now, you might say, this is fine, we'll run the PLL here, and it should work. And yes, it does work. However, you see that the range from here, this is 30 degrees, and this is minus 50 degrees. So this range here, where the PLL works stably, is only 80 degrees. If your PLL ever hops over this top here, then here the polarity of the feedback loop will be inverted. Your gains will be wrong, and the PLL will wander away. The same happens here. It will also run away in this direction. So actually, as a result, you have a very narrow range where your PLL actually works, and you have a strong tendency to wander away. These peaks can have different shapes. I've also seen, actually, more often you see this dip here behind the resonance peak. I've heard people talk about an anti-resonance, but usually it's not. In all cases that I've seen up to now, it was just explainable very well by crosstalk. A typical sign of crosstalk is when you're far out of resonance with in your amplitude sweeps, you're far away from resonance and you still see significant signal. When you still see more than 10% of the maximum peak signal while you're far away from the resonance, then you have a severe crosstalk problem that needs to be fixed. This can be fixed either by changing the wiring, or you can add a filter, things like that. But somehow this problem needs to be solved. Otherwise, your PLL will not be happy. The other issue that I'd like to discuss here is the DC offset, and I've talked about that already. And I showed you before that the DC offset in mixing will cause a peak at the cantilever resonance frequency. And if your cantilever resonance frequency is too low, then you might end up with a DC offset caused peak at F0. And this peak is much closer to the frequencies that we want to see, and it puts a much higher requirement on the filter, which makes the filter slower. So our 9 unit has an offset back that you can use to compensate out for the DC offset, which will remove this peak and will remove much of the distortion out of your images. Finally, in my talk, I'd like to show you some examples of more complex systems. And the things I'd like to show you are feature tracking, the Schwarzenegger feature tracking, and the sideband Kelvin system. This is the feature tracking. It has been referenced in other talks before. The idea is to circulate the tip over a kind of spherical feature on the sample. When this feature moves away, then the circle will get a slope, and we're detecting that slope here in a lock-in amplifier. So first of all, we have the standard AFM PLL with the topo PI controller that feeds on the Z, and then on the delta F signal, we feed that into another lock-in, and this lock-in has an X and a Y output that we use, and that X and a Y output is actually the slope of the circle. It comes down to, if you remember the Phasor diagram, there's an oscillation in X and there's an oscillation in Y, the sine and the cosine. Those are the X and Y components, and they both independently show the slope in the X direction and in the Y direction. I've shown you earlier how you detect slopes with the lock-in. These slopes get fed into PI controllers, and those PI controllers then create an offset that makes the system follow the feature on the surface. And this only works when you put an oscillator with an X and a Y output. In this case, I've drawn the two separate output wires because one gets summed into the X signal and the other one gets summed into the Y signal. Here on this oscillator, we really make use of the circling, actually of the spiral of the curve that I showed you earlier. That creates a circle above the sample, and our two PI controllers then sum in offsets to move that circle and follow the feature on the surface. And these two signals here, the X and Y outputs, can then be used to track or to create a track of where the feature went over the surface. The other thing that I like to show you is sideband Kelvin. It's a somewhat different way of detecting Kelvin probe signals. So again, we have a PLL here with a topo PI controller that gets to the Z piezo. The same signal that goes into the phase lock loop goes into a lock-in amplifier. What happens when you modulate the bias voltage between tip and sample, you get an interaction, and the interaction modulates the delta F. This shows up as two sidebands that are next to the cantilever resonance peak in the frequency plot. And what we do here is we're putting a lock-in onto that sideband. So the filter of that lock-in is made very, very narrow, so we don't see the main peak of the cantilever resonance anymore, but only the sideband peak. The F0 of this lock-in is not the same F0 as it's used in the PLL, but it's the F0 of the PLL plus the oscillation frequency of our oscillator. That makes us shift to the sideband position. The delta F then is the same that comes from the PLL, and that makes the lock-in shift its reference up and down slightly depending on whether the main peak of the AFM measurement moves up and down, because it can move. So this way, we're actually keeping the lock-in always exactly on the sideband frequency, and then we're measuring the X signal. We're using the X signal here, not the amplitude, because the X signal can be positive and can become negative. That's much easier for an input into a PI controller. The amplitude would only be positive. There has to be some phase shift done. There is actually a hidden phase control here that allows you to turn the reference phase of this lock-in, so all the signals in the X and we don't have any signal in the Y, and then this can be used as an input for the Kelvin PI controller, and the output of that Kelvin PI controller adds into the oscillation and basically nodes out the signal. This system or this setup has the advantage that the PLL bandwidth is kind of independent from the lock-in bandwidth. Actually, you can make the PLL bandwidth narrow enough so the PLL doesn't see the sidebands anymore, which makes a much cleaner topo image and which makes a faster measurement also. Okay, this is the end of my presentation. There are some references here that you can use for further reading. This first one is about instantaneous frequency. It's mathematically quite challenging, but explaining things very well. The second one is a book that I found on the internet by Mike Mead about lock-in amplifiers, which is quite nice to read. And then last but not least, there's many webinars on our website, on our RHK website, under this address, rhk-tech.com/support/tutorials. And this is the end of my presentation, and I thank you very much for your attention.